Hello everyone. In this video, we are going to look at the implementation of deep neural networks for solving classification problems using the scikit-learn library of Python. So in the previous video, we have seen the implementation of these deep neural networks for solving classification problems. So the idea will be almost the same with that of the previous video, with the exception of some differences. So when you say deep neural network, it has one or more hidden layers in between the input and the output layers. Then in the standard linear models, like that of linear regression or logistic regression, we have input layer and an output layer. So the difference here in the deep neural network is we are going to add one or more hidden layers in between the input and the output layers. And on these hidden layers, we are going to make certain nonlinear transformations on the values of these different nodes. If there is no linear or any nonlinear transformation to be done on the hidden layers, the deep neural network will be exactly the same with that of the standard linear regression model or the standard logistic regression model. So for today's implementation regarding that of a binary classification problem, we are going to consider data related to diabetes. So there are variables related to age, which is identifier, residence, age, height, sex, and so on. And here our outcome variable of interest is that of diabetes, whether the individual is diabetic or not. And all the other variables except this ID variable, which is the identifier, will be considered as inputs or covariates. So the first step in the pre-processing of the data is to split or to separate the input features and output features data. So let's separate first the input features data. So to separate the input features data, we need to exclude the ID variable, which has nothing to do with our analysis, except its own identification purpose, and diabetes, which is our target variable. So now the input features data is separated into a single data frame, and this input features data has 366 rows and there are 15 covariates starting from residence to time ppn. And for that of the outcome features data, we need to extract our target variable of interest, which is diabetes. So here we have one outcome variable diabetes, and this has also 366 observations. And next, we need to identify the quantitative and categorical covariates in the input features data. So first, let's describe the characteristics of the variables included in the input features data frame. Now here we have some objects with data type object. Here we have sex, residence, and frame. So here, as you can see here, this residence, sex, frame have values which are non-numeric, right? Then their data type in Python becomes object. All the other variables are numeric variables and their type become either int or that's of a float. So here for our particular case, all those variables which are not object type are quantitative variables, and the other object type of variables are going to be considered as categorical variables. So for the categorical features, we need to extract those variables with data type of object. So here we have three categorical variables, And for those quantity variables, all those variables which are different from object are quantitative variables. So here we have 12 quantitative variables. But here this code is applicable only for this particular dataset, because here I know that all the variables that are different from object data type are quantitative. Therefore, automatically those variables that are different from object data type are considered as simply quantitative variables. But this code is not necessarily applicable for any dataset. We have to be cautious to identify the categorical and quantitative features by inspection, because sometimes there could be a quantitative there could be a numeric variable with type, let's say, int or that of float, but that variable may not be necessarily quantitative. So a qualitative variable which is numerically coded is going to be treated as numeric, but that numeric variable is not necessarily quantitative. So here, in identifying the categorical features and the quantitative features, we have to identify them by inspection. We have to ensure that these variables are qualitative, and we have to ensure that those variables here are quantitative. So here we have 3 qualitative variables and 12 quantitative variables, and for those categorical or qualitative variables, we are going to encode them into a numeric variable, or we are going to use what we call dummy coding or one-hot encoding, and those quantitative variables are going to be either standardized or normalized. Then now let's split the data into train and test sets. And for that we need to import train test splits from sklearn model selection. Then we need to call this function and supply the input features and output features data and the test size. So now the split is done. Now this random state is for ease of reproducibility. Otherwise it doesn't have anything related to the train test split. So here we can see that there are 74 observations in the test set and 292 observations in the train set. And the other thing here, for example, it's better for us to inspect the distribution of the classes of our outcome variable. So YDF consists of our outcome variable of interest. So it has 2 values, 0 and 1. 83% belong to 0, or 83% of the individuals are non-diabetic, and about 17% of them are diabetic. So for now it's okay, but sometimes if the proportion of successes is very small, something like less than 5%, it is better to consider what we call a stratified train test split instead of a completely randomized train test split. So for that purpose we need to use this one, and here we have to add stratify equals YDF. Then if this proportion was in case something like less than 5%, like 3%, 2%, 4%, it's better to consider the split in a stratified way. So it's better to consider this stratification. But for our case, it's 3, 17, it doesn't matter, it doesn't have any that much difference. So I don't need this one for now. So the train test split is done. Next, we need to transform the input features. We have to, we are going to use one-hot encoding or dummy encoding for those categorical variables or input features, and we can use either standard scalar or minimax scalar for those quantity variables. And to transform both the qualitative and the categorical variables, in one shot, we can use this column transformer that can be imported from sklearn.compose. So the categorical transformer is one hot encoder, and the quantitative transformer is this minimax scalar. So we can do both transformations all in one. So column transformer, let's say categorical encoder, categorical transform, this is this one hot encoder for which variable for the categorical features. That is for residence, sex, and frame. And for the quantitative scalar, we need to use this quant transform, which is this minimax scalar. We can also use this standard scalar. And for which variables? For the quantitative variables or quantitative input features for these input features. So let's see, run this. Now this is just an instantiation. If I point to here, it's not fitted. That means the transformation is not done yet. It's just an instantiation for holding the transformations that you are going to apply. So the parameters are here, transformers. We have categorical encoder, this one, and quantitative scalar, this one. So for the categorical encoder, we have these three variables to be encoded, and for the quantitative scalar, we have these variables to be normalized or scaled. Then once we instantiate our transformer, next we need to call the method fitTransform over the training data. Then this makes a transformation for the training data. Now this is the transformation. Those qualitative variables are one hot encoded into or using values like 0 and 1, and those quantitative variables are normalized into a value between 0 and 1. Let's see the shape. It is there are 292 observations and there are 16 features. Now let's go back to here. Here there are 15 columns, right? There are 15 features. 15 columns, but here it becomes 16, right? Therefore here, for example, there is a variable which says frame in our data set. Frame, let's see the value counts. So here we have medium, small, large. So since this qualitative variable has three categories, taking one as a reference, this variable is represented by two dummy variables. Therefore, that's why here the number of input features in the transformer train set becomes 16, because frame is represented by two dummy variables. Then once we transform the training set, next we need to call the method transform and supply the training data. So here for the test data, here for the training data, we need to call this method fitTransform, but for the test data, we need to call this method transform. So for example, for those quantitative variables, the minimum and the maximum values of the training data are saved in the transformer. These minimum and maximum values of the training data saved in the transformer are going to be used for transforming the test data. So here instead of fitTransform, we have to call this method transform. Now the transformation is also done for the test data. So in the training data, we have 292 observations and 16 variables. 290 to 16 for the test. It's going to be, I can say dot shape. There are 74 observations, and 16 input features. So the shapes of both sets, the specifically the number of observations are the same between that of the transformed and that of the untransformed data sets, but there is a difference on the number of features due to the representation of the categorical variables having 3 or more categories. There will be a difference on the input features. And this is not a transformation, actually it's just a way of changing the data type. Here y3NDF is a panda series format. Now here just we are changing into an NumPy array format, and the same is true for this test data. Then in the training of the model for the regression problem, we considered MLP regressor, but now we are going to consider MLP classifier. Except this, everything else is going to be the same. So MLP classifier, let's go to the documentation of scikit-learn. So here this is not MLP regressor, but I have to change this, I think, to not MLP regressor. This one should be classifier. Classifier, and then this should be classifier. So let me click. Okay, yeah. So here this MLP classifier is by default having a hidden layer size of 100. That means there is one hidden layer consisting of 100 nodes, and the activation by default is ReLU, and the solver is Adam. The learning rate is 0.001, and so on. Then we have to instantiate the model using this class MLP classifier. Then over that we can call the method feeds and supply the training data to train the model, and we can make a prediction using the predict method and supply the input features data, and to obtain the score, which is accuracy, the default metric for classification problems, we can supply the inputs and output features of the data. And we can also look at the biases using this intercepts underscore attribute, and for the weights we can use this cofs attribute, cofs underscore attribute. So now let's import this MLP classifier from sklearn neural network. Now the MLP classifier is imported. Let's instantiate. To instantiate, what we are going to do is MLP classifier, then followed by brackets. So by default hidden layer size it is 100. So here we have one number, that means we have one hidden layer with 100 nodes. The activation function is ReLU, the solver Adam, it could be also SGD or stochastic gradient descent, and alpha is a learning rate. Now by default for estimating the parameters of the neural network model, first the parameters, that is the weights and the biases, are going to be initialized with a certain value. So for ease of reproducibility, it's better to specify the random state to a certain number, let's say 42. So let's save this instantiated model under the object name MLP classifier. So this is the instantiation of our deep neural network model for the classification problem. Now the model is not trained yet or fitted yet, but here the parameters by default we have 100 nodes of a single layer, a ReLU activation function, Adam or solver, and 0.001 learning rate, and so on. And if you are interested, we can look at the documentation of this MLP classifier. This documentation. just. Then once we instantiate our model of interest, next to fit the model, we need to call the method fit and pass the training data. So over this instantiated model, we need to just call this method and pass the training data. Now it says maximum iteration is 200 reads. So by default the maximum number of iterations, max iter, is 200. So 200 is not enough for this model now. Again here, just max iter, it is 200. Then we can set the maximum iteration, let's say, to 5000, and then fit our data on the instantiated model. So this will fit our model of interest. Now it is fitted. If we point to it's fitted, then we can look at the specifications. As usual, this is the maximum number of iterations, is 1. Now we can see the performance of the model using the score method and pass the training data to get the training accuracy, and we can call this score method and pass the testing data to get the testing accuracy. So if I run this, now the performance of the model on the training set is around 99%, and on the test it is around 92%. So here we can also examine the biases and weights. So now before that, let me go to now here in the input features data, we have 16 input nodes. We have 16 input nodes. So here, let me say there are 16 input nodes. And we have one hidden layer. That hidden layer is this one having 100 nodes. So let's say times 100 nodes. Then for example, for this case, the weights are going to be 16 times 100. There will be 1600 weights between the input layer and the hidden layer. And regarding that of the hidden layer and the output layer, in the hidden layer we have 100 nodes, and in the output we have one node for the probability of, let's say, success or probability of diabetics. So here the number of weights between the hidden layer and the output layer is 100 times 1. Just this is 100. So there will be 1600 weights between the input layer and the hidden layer, and 100 weights between the hidden layer and the output layer. We have also other parameters, that's of the bias. So in the input layer, in addition to these 16 input nodes, we have one bias, and we have one hidden layer. That hidden layer has 100 nodes. So 100 nodes. So here that means 1 times 100 biases are available between the input and the hidden layer. And regarding that of the hidden layer and the output layer, we have 100 nodes. Not 100 nodes. In the hidden layer, we are going to have one bias. This bias is going to be connected with the number of nodes of the output layer. But in the output layer, we have only one node. We have one node. So 1. So the number of biases between that of the hidden layer and the output layer is going to be 1 times 1. It's just 1. So let's see the intercepts first. So these are the intercepts of the model. So in the final layer, we have one intercept right here, one intercept, this one. But between that of the input layer and that of the hidden layer, we are going to have 100 biases. 100 biases. So from here, for example, let me just extract the first one. That is 0. Yeah. So here, let me say just shape. You see, so here, these nodes, these values are intercepts or biases between that of the input layer and the hidden layer. So here we have just 100 biases, and we have one bias in between the hidden layer and the output layer. And now let's examine that of the coefficients or the weights. Now here we have these match weights. So first we have these values, and another we have these values. So let's examine each one separately. I'm going to say here 0, and let me say just shape. So here we have 16 input features and 100 nodes in the hidden layer, right? So here we have 16 input features and 100 hidden layers. So 16 times 100, therefore this parameters becomes 1600. 1600. And let's consider the second one. Second one, we have 100 nodes and we have one output node. 100 times 1 is going to be 100 weights between the hidden layer and the output layer. So yeah, 100 times 1, it's 100. So we have this much of parameters which are not actually interpretable like that of the standard models. So now let's just consider different values of the hidden layers and then see the impact on the model performance. So let's specify the hidden layer size to 16. Now here we have just one number, then that means we have one hidden layer and this hidden layer has 16 nodes. And let the maximum iteration be 5000 and let the random state be 42. And let's train the model and get the performance on the training and testing sets. So with these 16 nodes of single hidden layer, the performance on the training is around 91%, and on the testing it is around 96%. Now let's increase from 16 to 32. So again here we have a single hidden layer consisting of 32 nodes. Now when we increase the number of nodes in the hidden layer from 16 to 32, the performance increases from 91% to 94% for the training set, and there is no much difference in between that of the test performance. And let's increase further from 32 to 64. Again you have single hidden layer consisting of 64 nodes. So let's train the model and get the performance on the training and testing sets. So now when increase to 64, the performance of the training data increases, but the performance on the testing data shows a decrement. And now let's increase the number of hidden layers. Now here previously here we considered one hidden layer consisting of 16 nodes, one hidden layer consisting of 32 nodes, one hidden layer consisting of 64 nodes. Now let's make the number of hidden layers 2, 3, and so on. So here hidden layer sizes 32, 16. Now here we have two values. then that means we have two hidden layers. The first hidden layer has 32 nodes, the second hidden layer has 16 nodes. So this is a two hidden layer deep neural network model. And let's fit as usual and see the performance. So this will result a performance of 99.7% for the training, and for the testing it's around 95.9%. So compared to the single layer models here, when we increase the number of hidden layers to 2, the performance of both the training and testing sets increase. And here we use 32 and 16 nodes. Let's increase this to 256 and 64. We have again two hidden layers, but the number of nodes of the first hidden layer increases from 32 to 256, and the number of nodes of the second hidden layer increases from 16 to 64. And let's fit the model as usual and get the performance scores. So as usual it will display, now the performance on the training set becomes 100% accuracy, and on the test it becomes 94.59%. So here when we have these 32 and 16 nodes, the performance was 95.94% on the test set, but when increase the nodes to 256 and 64, the performance on the testing sets shows a slight decrement, even if the training performance is 100% accurate. Similarly, we can also try a 3 hidden layer neural network model. 1, 2, 3. So that means the network has 3 hidden layers. The first layer has 256 nodes, the second 64 nodes, and the third 32 nodes. And let's train the model and then get the performance. So the first one is here just a single layer model, and we have a 2-layer model. Again here we have 2-layer model, and for a 3 hidden layer neural network model, the performance on the training is again 100%, but this performance on the test is somewhat the same with that of the previous one. So now let's see the difference between the standard logistic regression model and that of the deep neural network model. So this ML equivalent logistic regression. So what we are going to do here is, let me go back. Here by default this ReLU activation function is applied on the hidden layers. So a ReLU transformation is performed on the hidden layers. But if we change this to, let's say, identity, let the activation be identity, then that means even if you have one hidden layer, when you set the activation as identity, no transformation will be applied on the hidden nodes of the hidden layer. So if there is no transformation to be applied on the hidden layer nodes, that means even if this neural network has one additional hidden layer, this is exactly the same with that of the standard logistic regression model. So let me run it. Since I specify here identity, there is one hidden layer with 128 nodes, but this is exactly the same with that of a standard logistic regression model. So the performance is 89.7% for the training and 95.9% for the testing. And now let's fit that of the standard logistic regression model. We need to import logistic regression from a scalar linear model, and we need to instantiate the logistic regression model and fit our model and then get the performance. 87, 91.89%. These two values should be exactly the same, but before that, let me show you something. As we have seen in the previous video, the logistic regression model is by default a rich type of logistic regression model. It is not a standard logistic regression model. It says penalty L2, right? So if this penalty is considered, therefore this logistic regression model is not a standard logistic regression model. Rather, it is a rich type of logistic regression model. So that's why here this performance of the model on the training and testing sets are quite different from this one. So to fit the standard logistic regression model, here we have to set penalty equals none. So now this model is none, therefore this model is a standard logistic regression model. Therefore I have to specify this here and let me run it. Now you see 0.897, 0.897, 0.959, 0.959. Therefore, as long as no transformation is applied on the hidden nodes of the hidden layers, the deep neural network model is exactly the same with that of the standard linear models. So the same is true here. For example, if I remove this one, now there is no hidden layer. So this is the same with that of this regression model, standard regression model. So the idea is, in general, even if we have 2 or more hidden layers, let me say here 64. Let me say this and let's say 32. Now here we have 3 hidden layers, but we set the activation to identity. As long as this activation is identity, that means no transformation is going to be performed on the hidden layers of the model. So if no transformation is applied, this deep neural network is exactly the same with that of the standard logistic regression model. So let me run and see the difference. So there is no change, there is no difference, right? So the power of the deep neural network models comes from that of the activation functions. That means the nonlinear transformations that we make on the hidden layer nodes. So now let's tune the hyperparameters using a grid search algorithm like the one that we did in the previous video. Here we have hyperparameters number of hidden layers. When the number of hidden layers increases, that means the network becomes deeper. That is why we call it deep neural network. So as long as there is at least one hidden layer, we call the network as deep neural network. But when you have a larger number of hidden layers, the network is becoming more deeper. And in terms of the number of hidden nodes, when the number of hidden nodes increases, that means the network becomes more wider. And in terms of activation function, we can try identity, sigmoid, not sigmoid in scikit-learn. It uses the term logistic, but usually we call it sigmoid, but scikit-learn specifically uses this logistic activation function, tanh, which is called hyperbolic tangent, and rectified linear units or ReLU. In terms of optimizer, we have SGD or stochastic gradient descent and Adam optimizer. In terms of number of iteration, what we call epoch, we can also consider it as that's of unoptimal. That's what we can consider it as a hyperparameter. So like we did before, we need to instantiate this grid search CV, and once we instantiate this grid search CV, next we need to call the method fit and supply the training data to fit these grid search CV models. And to get the score, we need to call the method score, and CV underscore results underscore displays the summary results of all the models fitted using this grid search CV model. and best underscore params underscore displays the optimal values of the hyperparameters that we have specified, and the best score will be, this is just the average performance of the best model across the different folds. So to fit this grid search CV or to tune these hyperparameters, first we need to instantiate our model of interest. So here our model of interest is MLP classifier. Now this is just an instantiation. This is our model of interest that we want to fit. So by default here we have hidden layer sizes. We have one hidden layer and 100 nodes, activation ReLU, and so on. But we are going to change some of these hyperparameters. So let the param values be, for example, hidden layer sizes 32. That means here we have one hidden layer with 32 nodes. 64, one hidden layer with 64 hidden nodes. Here we have two hidden layers with 256 and 64 nodes, and here we have three hidden layers with 128 nodes, 64 nodes, and 32 nodes. In terms of activation, we have ReLU. Let's add another one. Let's say that's of logistic, and let me add another one, TAN-H. In terms of solver, let's specify SGD and ADA. Let the maximum iteration be 5000. So these are the specifications of these hyperparameters: hidden layer sizes, activation function, solver, and maximum iteration. So these are our specifications. Then once we specify these hyperparameter values, we can instantiate our grid search CV after importing it from scalar model selection. So for example, in terms of hidden layer sizes, we have 1, 2, 3, 4. 4 models. ReLU, Logistic, and TAN-H, 3 models. 4 times 3, 12. Here we have 1, 2, 12 times 2, 24. Plus times here we have 1, 24 times 1, 24. Therefore, these parameter combinations will provide 24 different models. So what the grid search algorithm does is it fits one model for each possible combination of these hyperparameter values, and then selects the ones that performs best. So let's import the grid search CV from scalar model selection. Then we need to instantiate our grid search models algorithm. So grid search CV, it needs the estimator or our model of interest, MLP classifier, this one. And param grid, we have parameter values. That is the specification of the hyperparameters. Here we have these hyperparameter specifications. Let the number of cross validations be 5. And by default, it only returns that of the test scores. But to get also the train scores, we can set this return train score to be true. So we can run this. Now this is just an instantiation. If I point to it, it is not fitted. So the grid search models, this object is not fitted yet. This is just an instantiation. So here, estimator MLP classifier. Here, the ones that we have specified, this one. This one is nothing but this one, MLP classifier. And here the parameter grid. You have activation, ReLU, logistic, hidden layer sizes like 32, 64, maximum iteration, solver. These are all the ones that we specified here. No, here in these parameter values. In number of cross validation, we specified as 5. Return train score, we specified it as true. So yeah, this is just the model of interest. So these values, some of these values are going to be changed based on the values that are specified here. Then once we instantiate this model, over this model, we need to call the method fit and supply the training data. Then this will try to fit all the possible models based on these possible combinations of hyperparameter values. So it may take a little bit some time. So now fitting the research models is completed. So these are the parameters that are specified before. You can click on this best estimator. So of the different possible combinations or of the different models, the model with a Tanich activation function and a 3 hidden layer model with 128, 64, and 32 nodes is the best model of the different 24 models. Here we have 4 models times here 3, that means 3 options. 12 times here 2 is 24. Therefore, we have here 24 possible candidate models. Of these 24 candidate models, the one with an activation with TANH function and hidden size of 3 is better. The other, we also specified that of the what you call the solver, right? So the solver is not mentioned here. That means by default, the solver is ADA. So this is the best model with this specification of the hyperparameters. We can get the CV results underscore. This is just a dictionary, but we can convert it into a data frame. So this displays results of each model. So totally we have here 24 rows. That means we have 24 possible combinations of hyperparameters. That means we have 24 models. So each row corresponds to the summary of that's of the different models fitted based on the different combinations. So again, the table is too large, so it's not easy to observe. So instead of all the columns, let's extract some of the columns related to hidden layer sizes, activation, solver, maximum iteration, mean train score, test score, and the rank. So these are some of the summaries for the 24 models. So the one that works best is this. So the one with 3 hidden layers, Tanich activation function, Adam optimizer, and this is 5000, the number of iterations or epochs. So this model with these specifications, the model will have a performance of 92% on the training set and 88% on the testing set. Therefore, of the different candidate models, this model is better. So we can find the optimal values of the hyperparameters in a deep neural network model using these research CV algorithms. So we can also extract directly that of the optimal values of the hyperparameters using this best params attribute. So over the research model, we can just call this. Therefore, the activation is TANH is the best one in terms of hidden layer size. This one, the one with 3 hidden layers, and iteration we have just one value, just 5000. And in terms of solver, Adam is better. So with this optimal hyperparameter values, the performance across the 5 different folds, because here we specify the number of cross validations to be 5. So this model with these hyperparameters, the performance across the 5 folds is obtained using this best score attribute. So it becomes 0.88. So we can also determine just the values of the the performance on our training set and the performance on our test set using the research models. So these research models automatically uses these optimal hyperparameter values. So I can run it. So the performance on the training set is 100% and on the test it is around 93%. So our optimal values here, number of hidden layer is a 3 hidden layer, therefore instead of 32 here I have to change it to 3 hidden layers. Activation, tan H is better, and in terms of solver, Adam is better, maximum iteration, yeah. So using this optimal hyperparameter values, let's fit our model again and get the training and testing performance. So we fit the model. This is the instantiation of the model based on these optimal hyperparameters because it corresponds to our final model. And let's get the train and test performance. So there could be some slight differences in the train and test. So 0.9093. Okay. Yeah, so there may be slight difference in the train and test performance, but should be the same. But actually here, the difference is here in the research CV. Here, when we instantiate the model, here we do not specify a random set. So each time the parameter values are going to be initialized randomly. Therefore, due to this random initialization, there will be a difference between these values. That is the train and test scores using the research models and the train and test scores using that of the actual model trained based on the optimal hyperparameters have some difference. And there could be also certain random set that the research algorithm uses internally, so that may have also an impact. Otherwise, this is our final model to be considered as the best model, or a three hidden layer model with a Tanich activation function and Adam solver is the better model. So lastly, let's see how to make a prediction. So to make a prediction, just over our fitted model here, MLP classifier, we need to call the method predicts and pass the training data, let's say. This produces the predicted values of the training data. If we change this to test, is the predicted values for that of the test data. Similarly, if we are interested, we can also we are interested on the probabilities instead of the actual classes. Now here, this predict method predicts the predicted class. So the value is either 0 or 1. But if we are interested on the probability, we can use this predict proba. Therefore, this displays the predicted probabilities. Here we have 1, 2. We have two probabilities. So the first one is for the probability of success, and the second one is no. The first one is for the probability of failure, and the second one is for the probability of success. Okay. So for example, here let's consider here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here we have at observation 14, the predicted class is class 1. So here let's consider 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's consider this one. Now this is the probability of failure or of 0. So this is 0.09, right? And this one so here First, let me extract the first 14 observations. That is, I need to say 14. Okay. So the last, I think this should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I think there is one more. I have to, this observation 14 is not being included. Okay, yeah. So this is the last observation is this one. So here we have 0 0.014, the probability. Here we have 0 0.85. Yeah, this is 0.85, this one 0.14. So this probability is larger. So the predicted class is here 1. So this is the predicted probability for the failure class, or let's say for class 0, and this is the predicted probability for the success class, or the probability of being diabetics. So if this is larger, the predicted class will be 1. Otherwise, if this is larger, the predicted class is going to be this one. For example, you have 0.99. This you have 0.000 something like 1. So this is larger, 0, 0, 0, and so on. But for this case, this is smaller than this one. So the predicted class is 1. So predict proba displays the of the probabilities of each category of the outcome variable. So lastly, if you are interested on the confusion matrix, you can also import it from the scalar matrix attributes, and you can display how it works. So on the predicted values on the test data, there are 2 plus 5, 7. 7 observations are misclassified. But all the other observations are correctly classified. So this is all about the implementation of deep neural network for solving binary classification problems. So thank you for watching.